Welcome to the Chemistry of Taste, where we show you how chemistry is the reason food tastes the way it does.
Today we are going to look at why things taste salty, sweet, sour, and burnt, and how chemical bonding and reactions control all of it.
Basically, your tongue is a detector that uses chemistry to pick up different flavors. So these are the ingredients we have. We have Morton iodized salt, we have baking soda, more baking soda, distilled vinegar, sugar, distilled water, 2 sizes of marshmallows, LED, which is what we're going to use for setup, and then the rest of our materials.
Today we'll be doing 3 experiments: salty versus sweet bonding, acid-base reactions, and heating and burning sugar.
And throughout the video we'll explain ionic bonds, covalent bonds, electrolytes, aqueous solutions, chemical reactions, thermal energy, and more.
So this isn't just taste test, this is chemistry controlling human taste.
From the naked eye, the salt and the sugar looks almost identical when you have them out, but just like white crystals, right? The same texture, but chemically they're completely different. And we're gonna start this experiment. We'll have NaCl plus H2O here, and C12H22O11, which is sucrose table sugar with H2O. And we're gonna pour a cup of distilled water into each. Right around 1 cup into the salt first. Perfect. So 1 cup of distilled water into each. Cut.
Table salt is sodium chloride, or NaCl, and it's held together by ionic bonds.
Sugar, or sucrose, is held together by covalent bonds, and the chemical formula for sucrose is C12H22O11. And as you can see, it's white crystally, just like the table salt.
All right, here we can see NaCl, or salt, dissociates into Na plus and Cl negative, making 2 ionic charged particles. And we see here C12H22O11 just stays whole in water, as when it does not dissociate.
All right, so now I'm pouring the salt into the water. Like that. Should be enough, and now I'm stirring it. So water is called the solvent, making this an aqueous solution, and the ions can move freely through the water, which makes salt water conductive.
Now I'm going to do the same thing for sugar. So I'm going to take a spoonful of the sugar and stir it. The ions can move freely through the water, which makes salt water conductive. But for sugar, as you can see, it kind of doesn't bind itself to the water, and you can still see the particles in the sugar water compared to the salt water, where the particles are nearly invisible.
This device is called a TDS meter, which stands for Total Dissolved Solids Meter.
It measures how many dissolved charged particles or ions are in a solution.
The more dissolved ions there are, the better the solution can conduct electricity.
This device is called a TDS meter, which stands for Total Dissolved Solids Meter.
It measures how many dissolved charged particles or ions are in a solution.
The more dissolved ions there are, the better the solution can conduct electricity. So now we're going to dip the TDS meter into the salt water and the sucrose water. So as you can see, when I dip the TDS meter into the salt water, the ppm is extremely high. Since the salt breaks apart into sodium and chloride ions in water, the salt water gives a much higher reading. These dissolved ions are what makes salt water conductive. Now, after rinsing the LDS meter off with tap water, I'm now going to dip it into the sugar water. As you can see, the reading is much lower than when we dipped it into the salt water. Sugar dissolves too, but it stays as neutral molecules instead of separating into ions. Since there are far fewer charged particles in the sugar water, the conductivity reading is so much lower.
All right, so here now we're going to do a small taste discussion.
So that in my left hand I have salt, and in my right hand I have the sugar.
So I'll start with just the salt. Oh! That is disgusting. The salt tastes salty because your tongue detects the ions, and that gives it the salty taste.
Here's the sugar. The sugar tastes sweet because the shape of the molecule fits into sweet receptors, almost like a lock and a key.
So now I'm going to have both at once, sort of like sunflower seeds if you get one of the flavors.
Salty sweet.
Salt sucks, but the sugar makes up for it. So even though these substances look similar physically, they're both white and crystalline, their chemical bonding changes everything about how they behave and taste.
Oh.
This experiment focuses on acids and bases. So for acids, we're using distilled white vinegar, and for our base is obviously going to be baking soda.
Vinegar contains acetic acid, which gives it its sour taste.
Baking soda is sodium bicarbonate, which acts as a base.
Take two, because I wasn't recording the first ones, but now they're going to taste test.
All right, so here's some vinegar. Taste test it real quick. Burns the throat. Before reacting, vinegar tastes strongly sour.
Where's the baking soda again?
Don't spit it on the thing.
Baking soda tastes bitter and weird because bases interact differently with your taste receptors.
Actual reaction between the acid and the base. So I already poured the vinegar into the cup, as you can see. So now I'm gonna pour the baking soda. And now, let's see. So as you can see, there's fizzing being produced in the cup, and this fizzing is actually carbon dioxide being produced by the reaction. This is a chemical change because new substances are being formed. The atoms are rearranging into carbon dioxide gas, water, and sodium acetate, and you can actually observe evidence of the reaction happening in the bubbling, the gas that's fuming up here, the temperature change, it's getting much colder, and the taste change. I'm not going to taste it, but if I were to, Colby wants to taste it.
It's like seltzer, or Alka-Seltzer. Ooh.
Colby,
It's
how did
much
that
more
taste?
mixed. It has a carbonated taste to it, but obviously it's much more in like a medial range compared to the acid or acidic and the base. This shows that taste can change completely after a chemical reaction.
The substances you start with aren't the same substances you'll end with.
Chemistry literally transformed the flavor.
Our last experiment will focus on heat energy and chemical change.
And honestly, this one's probably the best tasting.
Light her up.
Oh dear Lord!
Here we have a combustion reaction where we see sucrose combined with O2 creates 12 CO2 and 11 H2O.
Marshmallows are mostly sugar, and heat changes sugar chemically.
At first, the sugar caramelizes.
Caramelization is a chemical change caused by thermal energy.
The heat gives molecules enough energy to rearrange and create new flavor compounds. So now we have a raw marshmallow.
It was normal. Tastes normal. Sugary.
And now let's move on to the already burnt ones.
Oh, real burnt.
It's kind of falling apart.
Make sure you get the
As you
outer
can see, it's a lot more gooey,
crust.
liquidy. And when I taste it, it tastes like that
You can
typical
taste that
burnt
burnt, you
flavor.
can taste the burntness.
True.
If you keep heating it, combustion starts happening.
Combustion is a reaction between a fuel and oxygen that forms carbon dioxide and water.
You can literally see evidence of chemical change.
The black ashes and then the smoke when we were heating it, and the fact that it tastes, the taste is new and the smell is new. And the marshmallows were piping hot once we took it off the stove. The lightly toasted marshmallow tastes sweeter and richer.
The burnt one tastes bitter because the sugar molecules were destroyed and new substances formed.
So heat energy changes chemistry, and chemistry changes flavor. Throughout these experiments, we showed that taste is controlled by chemistry. Even simple foods and ingredients contain chemical structures and reactions that completely change the way they behave.
In our first experiment, we looked at salt and sugar. Even though they look almost identical physically, they behaved completely different because of their chemical bonding.
Salt is an ionic compound, which means it breaks apart into charged ions in water. Those ions were able to conduct electricity, which is why the TDS meter gave a much higher reading for salt water.
Sugar was different because it's a covalent compound. Instead of separating into ions, the molecules stayed intact in the solution. That meant the sugar water conducted electricity much more poorly.
That experiment showed that bonding affects much more than just structure. It affects conductivity, dissolving behavior, and even the way your body responds to different substances.
We also connected chemistry directly to taste. Salt tastes salty because your tongue detects ions, while sugar tastes sweet because the shape of the sugar molecules fits into the sweet taste receptors, almost like a lock and key mechanism.
Yeah, for sure. In the second experiment, we moved from physical processes into chemical reactions using vinegar and baking soda.
Vinegar contains acetic acid, while baking soda acts as a base. When we mix them together, the atoms rearranged into completely different substances.
We observed several pieces of evidence that proved the chemical reaction occurred, such as the bubbling of the reaction, the temperature change, the taste change, as experimented when Colby actually drank it, and the gas production when the reaction fumed above the thing.
The fizzing happened because carbon dioxide gas was being produced during the reaction. That gas escaping from the liquid, creating bubbling we could physically observe.
This experiment also showed how chemistry can completely change flavor. Before the reaction, the vinegar tasted strongly sour, and the baking soda tasted bitter and basic.
But after the reaction, the solution became much weaker in taste because the acid and base partially neutralized each other.
That demonstrates an important chemistry idea. When chemical reactions occur, the substances at the end are not the same substances you started with.
In our final experiment, we focused on thermal energy and chemical change using marshmallows.
When the marshmallow first heated up, caramelization occurred. Heat gave the sugar molecules enough energy to rearrange and form new flavor compounds.
But once the marshmallow started burning, combustion reactions began taking place.
Combustion is a chemical reaction between a fuel and oxygen that releases energy as heat and light while producing carbon dioxide and water.
And we could actually see the chemical change happen through the black ash that was produced after we heated it up. The actual heat that we could feel and taste in our mouth, the taste change and the color change, and the new smell, and it smelled burnt.
Yeah, for sure. The lightly toasted marshmallow tasted sweeter and richer because caramelization created new flavor compounds.
The burnt marshmallow tasted bitter because the original sugar molecules broke apart and formed entirely different substances during combustion.
Overall, every experiment in this project connected chemistry directly to everyday life and food.
Chemistry determines how substances dissolve, how they react, how they conduct electricity, and how they taste, most importantly.
The chemistry happening in these experiments is also happening constantly in cooking, digestion, and even inside the human body.
So even though chemistry is often associated with laboratories, equations, explosions, and whatnot, it's actually something we experience every single day.
Every salty chip, sour candy, toasted marshmallow, and sweet dessert depends on chemistry.
Taste is not just flavor, it's molecules, bonding, energy, and reactions interacting within your body.
Thanks for watching The Chemistry of Taste. Yeah.